Today we're going to continue our discussion of limits, and so far we've evaluated limits two different ways, numerically and graphically. You may or may not have liked either of those options, but this is our third option. Our third option is to evaluate limits analytically, or another word for analytically is algebraically, and I will tell you in advance I'm going to be using them interchangeably because they are used interchangeably in mathematics, algebraically and analytically. So to start with, we're going to take a look at some basic properties of limits. So when we have real numbers, b and c, and n is a positive integer, then the limit of, as x goes to c of b is b. And I'm going to kind of establish some of these from the perspectives we've already looked at. For example, if this is a constant, which is what it's supposed to be, it's like 5. What you have graphically is you have a horizontal line at y equal 5, right? If you have a horizontal line at y equal 5, the limit is always 5. It does not matter what x value you are at or are you approaching because you have a horizontal line. On the second one down here, you've got a limit of the graph y equal x. So our graph y equal x is one that you're very familiar with. It looks like this. At every x value, the y value and the x value match. So it seems quite reasonable that if the x value is approaching c, the limit, which would be the equivalent of the y value, would also be approaching c. Right? So x approaches c and y, or the limit, will approach c. This last one is actually an extension of the second one. It talks about if you have a polynomial, so if you have x raised to the power of n and you're letting x approach c, then you're actually letting that become the same as c itself. So c to the n is what you end up with. So what we're going to do is we're going to use these properties along with the next set to be able to evaluate limits with algebra. So our next set talks about how we combine limits together. So b and c are real numbers, n's a positive integer, just like in the last one. F and g are functions that have limits. Okay, they're going to exist. We're not going to have any sort of holes or breaks or anything like that, at least not near the point we care about. So if the limit for f of x as x approaches c is L, and the limit of g of x as x approaches c is k, then we can combine these in the following ways. So the first one's a scalar multiple. It says what happens when we have a constant multiplied by our function f of x. Well, in a very real sense, the constant just gets multiplied by the limit. It's what you would hope would happen. It's what you expect to have happen. The second one talks about what happens if you add these functions together. If f of x and g of x get added together or subtracted from one another, then their limits just do the same thing. So you see the L and the k getting added or subtracted equivalently. And the last one, the product, again, is what you would expect. So when you have two functions multiplied and they have limits, then if you're taking the limit of that product, you're going to get the product of the limits, L times k. So everything is exactly what you would expect it to be. The next two are a little different. So the next two talk about what happens when we have a quotient. So the quotient is very similar to the product. It's what you would think would have happened, but it has the extra sort of layer on there that you can't have the denominator to be 0, right? So the limit as x approaches c of the denominator being g of x means that my denominator cannot actually approach, or cannot approach to 0 because I'd be dividing by 0. The last one, the power one, tells us that the limit as x approaches c of f of x to the n is L to the power of n. Okay, everything good so far? All right. All right, so we're going to find the limit of some algebra functions. So we have the limit as x approaches 1 of a function negative x squared plus 1. While it's very true that we're going to apply all of these limit properties right here, they're just working behind the scenes. Okay, so the nuts and bolts of what we're doing is we're actually plugging the value 1 in for x. We're substituting it or evaluating it. So when we have a polynomial, this works really nicely because of all those limit properties that we discussed. This would be negative 1, negative, and then 1 squared plus 1. Just a reminder about exponents. The exponent itself applies only here to the value of 1 because x is 1. If the 1 were in parentheses like that, which it's not, then it would apply to the negative 1. So here we actually have 1 squared, so this would be 1, and then the negative on the outside of it, so negative 1, plus my 1, and my limit would be 0. On number 2, as long as when we plug the value in, the denominator is not 0, we are able to simply evaluate and plug the value in. So if I put the negative 3 in for x, what we really want to check sort of mentally before we start is that the denominator is not 0. Is it? No. So we're good to evaluate this. It will be negative 3 minus the 3 over negative 3 plus 5. What will my numerator equal? Negative 9. And the denominator? 2. There's nothing wrong with that particular expression of it. If you don't like the fact that it's an improper fraction, you're welcome to turn it into a mixed number or into a decimal. Any of them are equivalent as long as you have an actual answer, right? If it had, you don't want to approximate, in other words, so don't go rounding anything. But as long as you're not rounding anything, any of those versions are fine. All right, so far so good? Okay. Polynomials. I've mentioned the word polynomial already on the previous screen. The number 1 is a polynomial, number 2 is a rational function. So this theorem tells us what happens when we have polynomial functions and rational functions. So polynomial functions and rational functions have the same kind of properties. We're able to evaluate the limit algebraically or analytically by simply plugging the number in, substitution, unless the denominator is 0, in which case we can't do it that way. So the first part says if p is a polynomial function and the limit as x approaches c of p of x is equal to p of c. We can evaluate it, we can plug it in. Same thing for number 2, we have a rational function r of x is p of x over q of x. C is the number, and we can evaluate it by plugging the number in. So we have our function, which is p of x over q of x. We can put c in, so we have p of c over q of c. Okay, everything that we would expect to have happen is happening for us. It's not going to happen all semester, so appreciate it right now. Your intuition is leading you down the right path at the moment. And we have a couple more. I know a few of you are still writing, so let me pause for just a second. Okay, there's 2 more theorems about different types of functions. So far we've done polynomials, we've done rational functions. The next one is radicals. Again, the limit of a radical works the same way you'd expect it to. So if we have the limit as x approaches c of the nth root of x, it becomes the nth root of c. There are some conditions because radicals have conditions. If the index is odd, it doesn't matter what c is, right? So if you had a cube root or if you had a 5th root, c can be anything because you can take the cubed root of a negative number. That's really the kicker. But if n is even, right, like a square root, we have to have values underneath the radical that are positive. So you see the condition right here telling us that the c has to be greater than 0 when the index, the n part, is even. So square roots, 4th roots, 6th roots, things like that. Okay. Again, it's not really something to be worried about. Typically, that's not the question you're asked, but it is an awareness factor that there are some limitations. And then the last one for now, Theorem 1.5, talks about the limit of a composite function. So composite functions, if you'll remember, are functions that are embedded inside of other functions. So maybe you have like a polynomial that is underneath a radical. Or maybe you have a polynomial that is inside of something to, above and below a function. So like that's actually what a rational function is it's a composite function already. It has embedded polynomials inside of a ratio. So when this happens, and if you have the limit of the function g of x, and the g of x, and the limit of the function f of x, and g of x is embedded inside of the function f of x, so that's what you see happen right here, right? The g of x is inside of the f of x. Then what we do is we actually evaluate piecewise, and so we evaluate the limit of g of x And we were told in this case that it was L. And then we plug that into the function itself, f of x. So we're just evaluating both the functions. Again, everything that you expect to have happen is going to be happening. So you don't just have, right, a radical function. You can have polynomials inside of radicals. Or you can have rational functions inside of radicals. We can combine these kinds of functions together and we get more functions that we're able to work with. Okay, so let's do some examples. So again, our goal is to simply evaluate the function when it's possible. And when it's not, we'll talk about what algebra techniques we have to be able to change the expression to something we can work with. So if you were to evaluate, if you were to plug 3 into this one, it is a rational function, which means you need to pay attention to the denominator. And what do you notice if you try to plug the 3 into this denominator?
0.
Yeah, going to get 0 on the bottom, right? All right, that 0 on the bottom is a problem, right? It's in fact the thing that we said can't happen back when we talked about rational functions. Now, remind me your name? Adeline mentioned that it's 0 over 0. That's a really good thing to notice, because when it becomes 0 over 0, what it typically means is that there's some way that we can change the expression to be able to be still having a limit, or at least maybe. So what we want to do in this case is we want to see if we have any factoring that we can do. Now, in particular, the denominator has the ability to be factored. What will this denominator factor into?
X plus 3, x minus 3.
Right. It's called the difference of squares. It's x plus 3, x minus 3. Now, that's not identical to what's on top, either of those pieces, but it's awfully close. Which piece of the denominator is able to be reduced with the numerator in some fashion? Is it the part that says x plus 3, or is it the part that says x minus 3?
X minus 3.
It's the x minus 3. Now, x minus 3 is not the same as 3 minus x, but how are they different?
-1.
Yeah, they're different by a factor of -1. The signs are opposite, right? So instead of x being positive, x is negative. Instead of the 3 being negative, the 3 is positive, and vice versa. So I can, in fact, reduce these, and I reduce them because one of them will end up being a -1. It's just different signs. So if they're identical except for the signs, I'm able to cancel them, and I receive a -1 when I'm done. Now, as long as we still haven't plugged 3 in, we need to write the limit because we haven't actually evaluated it. So this is the limit as x approaches 3. And what I now have is -1 on top, and I have x plus 3 on bottom. I've changed the expression that I was given into an equal expression. It's exactly the same except for at 3. Otherwise, it's an identical expression. Just looks different. But now I'm able to plug the 3 in for x and get a value. What will I get if I plug 3 in for x here? -1 over 6. And if you wanted to confirm this, you could look at your graph, right? And you could get really, really close with the trace button. Or you could look at a table of values, and you could try values that are getting infinitely close to 3, right? 3.1, 3.01, 3.001. And what you will see is you will see the limit that you're getting as your output approaching -1 over 6. So this is our limit. Okay, so don't always just assume by looking at it that you necessarily have to factor. Sometimes you won't. But on this one, if you start, what you should be doing to start with is seeing whether or not that 4 makes the denominator 0. Does it?
Yeah.
It does. Okay, so if it didn't make the denominator 0, don't go through processes of factoring because you don't need to. That's just more work on you. So always check to make sure the denominator is actually 0 before you start worrying about factoring. Now, since the denominator is 0, we will attempt to factor both the denominator and the numerator because this one's a polynomial in both that has the ability to factor. So what will this denominator factor into? X minus 4 and x plus 2. Does everybody agree? That look okay? All right. How about the numerator? X minus 1 and x minus 4. Everybody agree okay with that piece? If you're a little rusty on factoring, that might be a good thing to go check with the Success Center and work through some extra factoring problems. We're not going to need it super intense all the time, but in this section, you're going to be using it. What do you notice reduces from the top to the bottom? x minus 4, and in particular, that x minus 4 was exactly what was causing the problem because it is the problem when I plug in 4 to make the denominator and the numerator actually 0. Right? If I put 4 into the top or the 4 in the bottom, that x minus 4 is going to give me 0. So what have I left with? Well, I still have the limit because I have not plugged in 4 for x. So limit as x approaches 4. On the top now, I have x minus 1. And on the bottom, I have x plus 2. Okay, so as you're working your way along, if you jump from the original expression that you were given here straight to the end, I have no idea how you did the problem. Did you look at a graph? Did you do it with numbers? Did you do it analytically, algebraically? So you have to show some of these in-between steps for us to know that you're processing through it with the analytical perspective, okay? All right, so at this point, can I actually plug the number 2 or 4 in for x? I can. So now I have 4 minus 1 over 4 plus 2, which will give me what? Yeah, 3 over 6, which is 1/2, which we definitely would reduce to the 1/2 like you guys did. Okay, any questions on that one? Okay, let me just talk briefly about number 5, but I don't want to do it. It'll take us longer than the 7 minutes that I told you we had remaining. If you try to do number 5 and plug the number 0 in, you definitely see the 0 in the denominator, right? Yeah, definitely. But this does not look like the last two problems. Agreed? Yeah, it definitely does not. There's no factoring of the numerator in nice polynomial types of ways that cancels with the x in the denominator. That's not what's going to happen. So this is kind of one of the classic tricks that we're going to do when we get to this one. And what we're going to do is we're going to remember something called a conjugate. Do you remember what a conjugate is for something? Let's do something simple. What's the conjugate for a plus b? A minus b. So we're going to be using the conjugate of what's on top, which will be the exact same expression as what's on top, but the sign different in the middle. And that's going to be the key to being able to change this algebraically to allow us to put 0 in for x. And we'll pick up there next time. So there's no homework due between now and Friday, right? Because we're not finished with 1.3. You'll have 1.3 to do over the long weekend that we have coming up.